Welcome back. In this section, we're now going to take a look at derivatives of the natural exponential function. So to start off with, we've got our theorem, and the theorem is telling us kind of an interesting result here that for e to the x, its derivative is itself. So kind of a natural consequence of this is if y is e to the x, then the first derivative is e to the x, and of course the derivative of that would also be e to the x, and then the derivative of that would also be e to the x. So in other words, e to the x, all of its derivatives are itself, and in fact, since e is continuous and differentiable everywhere, so would the first derivative be, and so would the second derivative be. In other words, e to the x, you can differentiate it as many times as you'd like, and it'll always be e to the x. The second little statement here is basically just chain rule application. If we had, instead of e to the x, we had e to some function of x. So that the proof of that's pretty quick. I'll do one, though, the proof of that, and I'm going to actually do it twice because there's two kind of nice ways to show this. One way uses the previous theorem that we had in 5.3 rather, the derivative of an inverse function. So let's start off with, let's suppose we've got f of x being our function natural log of x, and let's say we're interested in our inverse function e to the x. And so what we want to know is what is the derivative of f prime. We want to know what's the derivative of e to the x. And the previous theorem said, well, that would be 1 over f prime of f inverse. And in other words, that's 1 over f prime of f inverse. In other words, 1 over f prime of e to the x. F is natural log of x, so f prime is 1 over x. So f prime of e to the x is 1 over e to the x, which gives us just e to the x. So that's one way to show it. So this is by our previous theorem, and we were able to use that previous theorem because we knew natural log had an inverse, and we also knew that natural log was differentiable everywhere, and in fact not equal to 0 anywhere for its derivative, which means that e to the x will have a derivative everywhere. So there we go. That's one way to show it. Or another way that we could show it is to look at this statement, which is a true statement for sure. We could say that natural log of e to the x for sure is equal to x. And that's true because of the inverse properties. We're putting an exponential function into a natural log. They are inverses. They'd cancel each other out. And so if you ask yourself, what happens if I differentiate both sides with respect to x? On the right side, I mean, we know how to do the derivative of natural log. It would be 1 over whatever its natural log of, and then we'd have to do the derivative of the inside, and we don't know what that is. So I'll just write that it's whatever it is the derivative of the inside. So I have 1 over e to the x times whatever the derivative of e to the x is, and I don't know what it is yet. On the right side of the equation, I've got derivative of x, which is just 1. And if I were to take this equation and rewrite it, if I were to bring the e to the x up to the other side, I would have that the derivative with respect to x of e to the x is 1 times e to the x, which is just e to the x. So either way, I wind up with the same conclusion. So one way using the previous theorem, another way using the inverse property and a little bit of differentiation. One other little thing that I can say here, if we were thinking about the proof of 2, now that we've shown that 1 is true, 2 is kind of automatic because of chain rule. If you're looking at the derivative of e with respect of e to the u with respect to x, you'd have the derivative with respect to u, which is just itself, times the derivative of u with respect to x. So this is really just a chain rule repackaged using the derivative of e to the x. Okay, so now let's use this and let's find some derivatives. For the first one, fairly straight ahead, I've got y as an exponential function, e to the power of, and so for the derivative of it, I would just say, well, that would be e to the power of, and then multiplied by the derivative of the power. So this, just as I'm writing it down, you'll notice I didn't originally have brackets, then I put some on to make things a little bit clearer, and I even put brackets around the exponential function. You wouldn't be wrong if you wrote it, for example, like this, without brackets. Here, let me redo this again. And only had put brackets around the 2x minus 3 side of things. I find this, for myself at least, this is a little hard to read, that it doesn't quite look like these two things are being multiplied together because of the huge gap between the e and the bracket. So typically you'll find that I, along with most people when they type math text, will put the polynomial part in front of an exponential function, and it just looks a little bit nicer. And so that's, you're going to see me doing that again and again, sort of rewriting things and sticking the e at the very end. Other thing that you'll also see me doing is using some exponential properties that we know to clean things up. So if I'm looking at this second function f as it currently stands, this is a quotient, right? So I would have to use quotient rule, which, I mean, it's definitely possible and feasible for me to do, but I kind of don't want to. It would be maybe a little bit nicer if it was just as a product, and that's easy to do because we know that e to the x squared in the denominator would be e to the negative x squared in the numerator. And so instead of having a quotient rule, now I'll just have product rule, and that's a little bit nicer. First thing as it is, derivative of the second. And for the second thing, it's e to the power of. So I'll have e to the power of, power as it is, and then multiplied by the derivative of the power, and the derivative of negative x squared is minus 2x. And then I'll have plus the second thing as it is times the derivative of the first, and the derivative of the first function, derivative of x, is 1. The one thing you'll notice here, and this is a common theme, because e has itself as its own derivative, then in product rules and quotient rules, if you had e will just show up everywhere. So specifically, I've got an e to the minus x squared that happens to be in both of my factors. So I will take the e to the minus x squared out, and that's going to leave me with a minus 2x squared and a plus 1. So I'll have 1 minus 2x squared times e to the negative x squared as my derivative. Okay, let's do another one. We've got some trig functions now, and so let's do derivative again. This is a product, so product rule. First thing as it is, derivative of the second. Derivative of sine is cosine. Derivative of cosine is negative sine, and then plus the second thing as it is times the derivative of the first. And the derivative of e to the x is e to the x. And again, I've got two really big terms here, and both of them involve e to the x as a factor, so I can take e to the x out. And then what will I have left? I have a cos x minus a sine x plus a sine x and plus a cosine x. All that cleans up to give me 2 cosine x. So I get 2 cosine x e to the x as my derivative. Okay, last one on this page, we've got a function inside of a function inside of a function. So I have cosecant inside of an exponential function put inside of secant. Okay, so let's find our derivative. dy dx, what's the derivative of this function? So working my way from outside to inside, derivative of secant is secant tangent, and leaving the insides alone for now, so that'll be an e cosecant of x inside of both. And now let's do derivative of the inside. Derivative of the inside, that's the e cosecant of x. Derivative of e is itself. Okay, leaving the power alone for now. And now derivative of the power, derivative of cosecant x, that's negative cosecant cotangent. And then I guess probably the only last thing I would do is just rewrite it so that I don't have the negative kind of stuck at the end there. So minus cosecant x, cotangent x, secant of e to the cosecant x, tangent of e to the cosecant x, all multiplied by another e to the cosecant x. Okay, so we've done a few derivatives, and let's look at some more complicated problems. Some tangent line stories, maybe coming up with increasing and decreasing and maxes and mins and all the rest, because of course all that's on the table now. One thing you're going to want to do, as always, as I said this when we were looking at derivatives of natural log, same thing is true when exponential functions are at play. You'll probably want to do some sort of simplification if possible. Right now, if I'm looking at this, I can see that I've got a function inside of a function. I have all these e to the power ofs inside of my natural log. So that's definitely going to be a chain rule. And then when I do the derivative of the inside, that's going to be a quotient, and I'll have quotient rule to deal with. There's a couple of ways that we could possibly rewrite it. So one way might be if I were to think about splitting this up into two fractions inside, 2 over e to the x and minus e to the x over e to the x. And that at least makes it a little bit less terrible for me. I'll have natural log of 2e to the negative x and then minus 1. That's maybe a little bit better. The other option that I might consider doing might be to take what I have here, this 2e to the minus x over e to the x, and use my natural log property and say instead f of x is natural log of the numerator minus natural log of the denominator. And then for that, natural log of e to the x is just x. And you could differentiate whichever one of these you please. You're going to find that they wind up getting you two equivalent derivatives. So even though these functions look different, either way you're going to wind up finding that f prime for this function and f prime for this function are equivalent. Here I'll show you this for both of them. For the first function, if we wanted to find the derivative, if I had simplified it into this form, I would have natural log of all this stuff. So derivative would be 1 over all of that stuff. And then multiplied by the derivative of the inside. The derivative of 2e to the minus x would be, that constant multiple will stick around, and derivative of e will be itself, multiplied by derivative of the exponent, and derivative of minus x is negative 1. And derivative of the minus 1 would just be 0. So I would wind up with minus 2e to the minus x over 2e to the minus x minus 1. And if I wanted to make this look a little less terrible for myself, because I've got all these e's to negative powers, if you were to multiply top and bottom just for fun by e to the x, then in the top you'd have minus 2 just by itself, and in the bottom you'd have 2 minus e to the x, and that looks a little bit less terrible, I think. If you had used the second version of simplification, if we had f of x written like this, if we took our derivative, we'd see that we'd have for natural log of 2 minus e to the x, we'd have 1 over 2 minus e to the x, and the derivative of the inside, derivative of 2 is nothing. The derivative of minus e to the x is minus e to the x. And then for the last little term there, the derivative of x is 1. So we have minus e to the minus x over 2 minus e to the x. Whoop, correction. I threw a negative into the exponent where there wasn't one. It was minus e to the positive x over 2 minus e to the positive x. There we go, minus 1. If I decided to take this minus 1 and combine it with this first fraction, I'd have to make common denominators. So I would do that. And if I did that and then combine the two fractions together into one, you'd see that I'd have a minus e to the x minus 2 and minus a negative e to the x, or a plus e to the x. The minus e to the x and the plus e to the x would cancel, leaving just a minus 2 on the top. So either way, we wind up having the same derivative. So kind of fun. Okay, so now let's use our derivative for good. We're interested in finding the tangent line at when x is equal to 0. Either way, when x is equal to 0, our derivative would be minus 2 over minus 2 over 2 minus e to the 0. E to the 0, we know that that should be 1. And that would give us negative 2 over 2 minus 1, which is just negative 2. So our slope is negative 2. As far as what is the y value for this, so we found our slope. I guess I should have also found at the beginning of this my point. I know that the x value is 0, and for this, the y value should be f of 0, which is natural log of 2 minus e to the 0 over e to the 0. E to the 0 is 1, so when we clean that up, you'll have 2 minus 1 over 1, which is just 1, and natural log of 1 is 0, so in other words, the point that we're at is 0, 0. So our line goes through the origin, and it's the line 0, 0, it's the point 0, 0 rather, with slope of negative 2, so for our line, using my point 0, 0 and my slope, I would say y minus the y coordinate equals slope times x minus the x coordinate, or the line is just y equals negative 2x. And there we go. That's my tangent line to that curve at x equals 0. All right, we could also have implicitly defined things, so that's another way which we could have further excitement. Another tangent line we want to do this time at the point 1, 1 for this equation. I'm going to do some simplification here for sure, so I can see that I have natural log of a product on that left side. I don't want to have to deal with product rules, so I'll use the natural log properties to turn it into natural log of x and natural log of y. And on the right side, I technically have a quotient, and I can fix that by using my exponential properties and saying, well, that should be e to the x minus y. And now I'm going to differentiate both sides with respect to x. So anytime I differentiate things involving y, I need to remember that y is a function of x, so there'll be a dy dx popping up. The derivative of y is 0, and the derivative of natural log of x is 1 over x. The derivative of natural log of y would be 1 over y times the derivative of y. For derivative of e to the anything, it's itself multiplied by the derivative of its exponent. And the derivative of its exponent, the derivative of x is 1, and the derivative of y is dy dx. I'm not going to bother simplifying this and trying to solve for dy dx. I just need to find my slope, and I know what point I'm using, so I would just go right ahead and say at that point of 1, 1, we would have 1 over 1, which is 1, plus 1 over 1, which is 1 times dy dx, equals e to the 1 minus 1, e to the 0, that's 1, and times 1 minus dy dx. So in other words, what have we got? I've got 1 plus dy dx equals 1 minus dy dx, or 2 dy dx is equal to 0. So in other words, our slope is 0. We've got ourselves apparently a horizontal tangent line at that point 1, 1. And so now we can say for our line that the line should be y minus the y coordinate equals slope x minus the x coordinate. Or in other words, our line is just the horizontal line y equals 1.